which is kind of glorified postdoc in the group of quantum complex systems with Klaus Richter. The name Klaus Richter maybe popped around last week when we were having this nice introduction to what we call single particle quantum chaos. And this week starts the many varied aspects of quantum chaos. And first of all, thanks Barbara and Hilda for the invitation. I'm really honored to be here. And so, if I understand correctly, I'm the first one using the Blackboard, and the plan is more or less the first 2 sessions I will give, the ones of today, are planned to be kind of a lecture, and so that's why I thought better the Blackboard. And the session of tomorrow will be applications of semiclassics in Fock space. And this I will, of course, present you a bunch of results from papers and stuff. And okay, so let me tell you what is the plan for today and tomorrow. Can you read? Great, okay. So, the first thing is that I will review certain aspects of path integrals in single particle first quantized systems that I know that the seniors here of my generation know very well, and I guess many of you also know very well. But I will repeat because I need to stress certain aspects of path integral methods that are important for semiclassics. So we will start with a very quick of some aspects of path integral methods in single particle systems. And well, in particular, something that I will need to take path integrals from the standard formulation for single particles in configuration space to take all this machinery into the Fock space of quantum fields or many varied systems. We need to remember that there are kind of 2 formulations there. I call it, the Lagrangian kind of version and the Hamiltonian. Thing is, as we are going to learn, the Hamiltonians we have to deal when we describe interacting many varied systems in second quantization are quite ugly. So they are not p squared over 2m plus potential depending on the coordinates. They are more complicated than that, and then the usual approach cannot be handled easily in this situation. So we need to introduce this version of the path integral that we call the Hamiltonian. There is nothing mysterious there, but I just want to refresh you on that. Then we are armed with this Hamiltonian formulation, and we are going to reintroduce, because I know you have seen this last week from people that know this very, very, very well. We are going to introduce shortly the semiclassical approximation. And in this context, in single particle systems, I will call the corresponding semiclassical approximation the h bar going to 0 version of semiclassics. This distinction will be important because when we go to Fock space, we will find out that semiclassics is not defined, or the classical limit is not defined through h bar going to 0. It's defined in some other way. And that's one of the cute aspects of many varied semiclassics. Well, this will be short because this is something that Martin did last week way better than anything I could do. And now we have our, well, the semi-classical approximation to the path integral. We will understand what is the semi-classical approximation in that sense. Now we will make the jump. We are going to introduce the basic concepts of how to describe interacting bosonic systems using path integral methods. So I will write something here, and some of you, I hope no one, but if someone gets scared, don't be scared, okay? So look, I will introduce the path integral for discrete bosonic fields. Don't get scared. What I mean by discrete bosonic fields is the Hamiltonian that you see describing cold atoms in optical lattices, what is called the Bose-Hobart Hamiltonian, which is some combination of creation and annihilation operators. No need to be scared, okay? This I stress more because if you go to a field theorist, like some of you most likely are, eventually would like to do field theory, discrete bosonic quantum field is the cheapest quantum field you can imagine. I mean, it's not QCD, there are bosons, which are easier than fermions. They are discrete, meaning in the lattice, not in the continuum. And so it's kind of the simplest thing you can do when you introduce quantum fields. Tomorrow, I will tell you what do we know about going beyond discrete bosonic quantum fields doing semi-classics, like continuum or fermions and all that. Very important, extremely important. I very much prefer to go very slow than someone gets lost. So please, the moment that you get confused, there are no stupid questions here. It took me years to understand these things, so I understand the suffering and pain sometimes. So please ask me any question. I will be super happy to answer, okay? Anything. Okay. Once we introduce our path integral, which is still not semi-classics, it's an exact description of the quantum mechanical propagator. To introduce this, I need to introduce basic concepts of discrete bosonic fields. It's a machinery that you are familiar with because it's the machinery you use to quantize the harmonic oscillator. Well, now it has a different name, bosonic fields, but it's a bunch of harmonic oscillators and eventually non-harmonic oscillators. But we need to introduce the kinematics, meaning what is a state of a bosonic quantum field? What is the Hilbert space? Which are the bases? Which operators I define there, and all that. So I will introduce the concept of Fock space, creation and annihilation operators, all the kinematics there. And once I introduce the kinematics, I will introduce a particular representation in the bosonic Fock space, which is called the quadrature representation. Which is if any of you here is doing quantum optics, in quantum optics they do this all the time. So it's like reintroducing position and momentum operators in this space, but we will get there. And in this quadrature representation, with the help of this quadrature representation, I can really formulate very precisely, very nicely, the path integral. So we will construct the path integral here. And once we have the path integral in quadrature, I have to come back to the physical Fock space. So we have to project on Fock states. That's difficult. And once we do that, we have a path integral in the space of physical states of bosonic quantum systems. Okay, now this field here means that we are describing systems with many degrees of freedom. And then with this machinery, we can pose the question, what happens with all these concepts when the number of particles is large? And then what I'm going to at least justify is that the limit of large number of particles of a bosonic discrete quantum field plays the role of the h bar going to 0 in single particle systems, meaning I can build a semi-classical theory of these systems when the number of particles is large. And so we will do the asymptotics and all that. And we have to understand what are we talking about. So we have to understand to give a physical picture and interpretation of this limit, and this we are going to do. What is the classical limit? What do I mean by that? And that's kind of the highest point here, the derivation of the semi-classical propagator in Fock space for large number of particles. And then we are going, once we have that, we can kind of mimic what has been done in single particle systems, and in a very, very explicit way, show how to look for interference effects in Fock space. Interference of what in Fock space? So we will have a picture of interference from single particle systems, and we will kind of extend it into Fock space, which is kind of more abstract place. And so there is a line here, because up to there, everything I will do is completely general. It's valid for systems which are integrable, chaotic. It's a completely general machinery. At this point, I will show how the concept of chaos in the classical limit of bosonic discrete fields allows you to calculate things. So finally, we will do applications. And then I will show you theoretical predictions relying on chaos. So for this, I will rely on the classical field chaos aspects of the classical limit of this theory to calculate things, which is what we like about chaos. It allows you to calculate things. And so I will show you some applications of coherent phenomena in Fock space based on this machine. This will be tomorrow. This is the third session. Let's see if today, in the two sessions that we have, we make it up to here. That's the goal. As I say, I don't care if we make it only halfway. You ask me any question that you have. So let's start. Need to make this bigger. So no shame in asking, no shame in answering. Who has taken a lecture of quantum mechanics where you saw the derivation of the Feynman path integral? Can you raise your hand? Almost all of you, right. This is what I thought. So you guys, you girls that are already seen that, this will sound like a repetition. For the ones that haven't seen it, well, I will try to put the basics together in a nice way. So I will define what is called the propagator depends on three arguments: initial position, final position, and the time. I will make some assumptions here. I have a system of one particle, 1 degree of freedom, with orbital degrees of freedom. So I'm not talking about one spin, talking about one electron in space. 1 degree of freedom in real orbital space, described by a Hamiltonian which is independent on time. We will generalize everything later, but so one particle, time-independent Hamiltonian, and this object is defined as the matrix element in position representation of the time evolution operator. It's that simple. And so according to the postulates of quantum mechanics, this thing has an interpretation. First of all, it's an amplitude. That's very important. This is not a probability, it's an amplitude. Therefore, doesn't have a classical limit. That's an important aspect of this. And the interpretation is, if I prepare my particle to be at the position Q initial, meaning I measure the particle at time 0, and I find it in T initial, in Q initial position. Okay, then I let it evolve in time under the Hamiltonian, and then I project in Q final. This is, according to the postulates, this mathematical object represents the probability amplitude to measure the particle at Q final at time T if I measure the particle at time 0 at Q initial. This is just postulates of quantum mechanics. I don't need to go into detail there. And now the standard way to proceed is to decompose this object in pieces. Let me be consistent with, no. Okay, you did. Okay, this is what I thought. And so I can write the path integral, do you think? I can write the, probably I. Okay, so you are seeing this for the third time now. I'm sorry, but probably I will stress certain aspects, and Martin is stressed, and Barbara is stressed, and certain other aspects. So let's go quick. No, let's write the. But did you do the? I should have asked you before. Okay. Question: did you do the Hamiltonian form or the Lagrangian? The Lagrangian, okay. And so I need the discrete version to do the Hamiltonian anyway. So I will go for it. Sorry, guys. Technical remark. So first, I will split this object in n pieces. I'm doing nothing there. This is an exact step. And then what I'm going to do is consider the behavior of this quantity for a very particular type of Hamiltonian. So now, this is the Hamiltonian non-relativistic particle that spinless non-relativistic particle that we know and love. But as I have told you, in this bosonic field, you easily find things with p to the 4. And then you have to rethink this derivation of the path integral I'm doing here. But for this guy, then one can show that some matrix element of this object. Let's be pedantic and very, very explicit. And this V function of the Q operator, I will call V operator. Just remember that it only depends on Q. Now, there is some mathematical results that are dangerous to apply in this case, but at least there is kind of, you can expect the following. If you remember, well, one is super tempted to divide this exponential in two. You cannot do that because these are operators, they don't commute, all that. But if this epsilon is very small, you can use something that is called Baker-Hausdorff expansions, and it's kind of expected the following. Plus something that goes to 0 when epsilon goes to 0. And now, how precisely this happens, what is the type of error you are making there, that's a complicated story. But at least under some assumptions, this thing holds. And well, some mathematicians really suffer when you do these things, but that's the idea. When epsilon goes to 0, meaning when the number of partitions goes to infinity, the error I'm making when I do that is I can keep, in some sense, small. Now, if you swallow that is a big thing to swallow, then you will split each of these little, it's here. Each of these little time evolution operators, you split like that, and you realize, every time I have a position state nearby a potential, I know how to calculate that. For example, in this case, this part will be your Q prime, and since the potential is only function of the position operator, this spits out a number, the potential evaluated at Q prime. And this is kind of what you can think about the path integral in the long term as an attempt to do quantum mechanics without operators, without hats, and all these things don't commute. We will end up with a formulation which depends only on functions. I'm doing integrals of functions, no operators, nothing like that. And so this is a step in the right direction. Every time I have a combination like that, I obtain a scalar object, a number, not an operator. Sounds good. Now I have to do that all the way. So the trick to do that all the way is to, in each of the terms of this product, insert, so I will do it here, I will insert a bunch of realizations of the unit operator So I have one of these, I start with this, let's start here. Start with Q initial, it hits one of those guys, I do this trick. Then I have the next piece of the time evolution operator, I insert one of those, I use that trick, and go. And I do that n times. And is everyone following this? Great, thanks to Martin and Barbara, we are doing fine. So I will write two things that you usually do when you insert all these evolution operators. Eventually, we will have a lot of exponentials with the potential evaluated at arguments that are here appear as integration variables. And the other factors I will get when I do that are of this type. Remember, T is the kinetic energy operator, P squared over 2m. I will have a lot of integrals like that, probably with J and J minus 1 here, or J plus 1 here and J here, but I will have a bunch of objects like that. What we usually do to derive the Feynman path integral is to evaluate this guy. Well, it's luckily, this is known in closed form. How do you evaluate a matrix element of an operator that is a function of the momentum? You insert a unit representation of the momentum. So I will do it. Let's do it slow. Where is my epsilon? Sorry. There is an epsilon here. And here, I will insert a unit representation of the momentum. Let's do like that. And my Q prime. Okay. Now, the integral is linear. I put everything out. Integral over momentum. The T operator acting on an eigenstate of the momentum just gives me this function evaluated at the corresponding label of the state. So this will be the Q I have on the left. When this fellow acts here, gives me epsilon p squared over 2m. And P and P Q prime. Good. Now, this is just a number. So the P goes through. I will put, these are just numbers, you know. I don't have any operators, anything. This is just an integral. These are known functions. I will write them. Because I know what's this. I know this is 1 over the square root of 2 pi h bar e to the I Q P. Okay? Now, this is just an exponential, linear in the momentum. This is quadratic in the momentum. This means that this integral is a Gaussian integral that can be solved. And this is what we usually do. We solve this integral, and the result, so I can solve it, and the result is this. I always forget the right prefactors. Yes. Okay, so at this point, we have managed to do something remarkable, which is instead of calculating the time evolution operator using operators and things that don't commute and all that, we found an expression for the approximation to the propagator when you split it in n pieces in terms of a bunch of integrals over all these possible QJs I'm introducing, and that's it. I mean, there is no operators, there is nothing else, and when I put this result together, which you did yesterday, sorry for repeating, so I will call it the nth approximation to the time evolution operator. You can ask me, why is this an approximation? Where is the approximation? The approximation is here. Never forget it. I'm assuming that when epsilon goes to 0, when n goes to infinity, somehow I can control the error I'm making there. That's a non-trivial statement, okay? But there are some efforts to do it right. And the nth approximation, how does it look? I will now put everything together and write it in a way that is suggestive. every integral I'm writing goes from minus infinity to plus infinity. So I have the bunch of integrals, representations of the unit operator I introduce all around here in order to end up with these matrix elements, which I know how to calculate. So I have all of them. And then I have something very cute here. The indexes are important here. 0, n minus 1. Where did I put the epsilon? At the end. That's it? Ah, thank you. Thank you, thank you. I see that you are paying attention, and Martin is paying attention. So very good. Now, please. Epsilon. And somewhere else, look. I mean, look at the arguments, initial, final, and time. So first question, where is the time? The time is in epsilon, t over n, quite cute. Where is q initial and q final? Something that some books go kind of too fast, by the way. Fully recommended. It's double n. It's double n, one n. The Schulman book on path integrals that is this big and has everything, I mean, almost everything that you need to know. And the other Bible of path integrals is this big. It's the Hagen-Kleiner book on path integrals, and it's completely useless because he introduces his own methods, his own notation. You need to read all the book to use it. The Schulman book is really fully recommended. I will send a list of references for you. But path integrals, Schulman is great, and there is some a book from Orland Negele. It's called Quantum Many-Body Systems, and it's also a fantastic book to understand all these things. Okay. Now, you should realize that the integration starts at 1, but I have a Q0 here, where the identification is Q0 is Q initial. And you see, there is a Qn here, but there is no integration in Qn. This is because Qn is Q final. Okay, and please. Oh, thank you. Jesus Christ, of course. And that's the brilliant realization of Feynman, precisely. Feynman, he wanted to do quantum mechanics without Hamiltonians. He wanted to do quantum mechanics with Lagrangians. And there is the Lagrangian. Of course, was Dirac who told him, hey, it seems like in the transition amplitude there is something like an action, which is the integral of the Lagrangian. And okay, that's the realization of that. Of course, we are assuming here that when n goes to infinity, this thing, whatever it is, kind of reflects the original quantum mechanical object. That's hard to prove, okay? That's a big statement. But assuming that, which is a strong assumption, assuming that in some sense, at least, then we will brutally take the limit n going to infinity here. Brutally, okay? And so it will be this, look what is n here. Epsilon is 1 over n. So you have something like n to the n here. This n to the n, together with the product of differentials, I will call a functional measure. So this is a symbol to represent the limit when n goes to infinity of this combination of symbols. Very important, pretty much as happens here, this thing is subject to conditions. I will use S as the time variable. T is the total time, and S is kind of the integration time variable. So this monster represents that. And what is left is to put here, well, the continuum version of that for decent potentials and all that, well, you recognize a Riemann sum. So this is and if you remember your lectures in classical mechanics, you recognize this object as what? First question for, well, what is inside is the Lagrangian. And with the integral, which action? There are many actions. Which action? Yeah, you're right, the action. Which action? Someone knows the name I put on it? That's the action functional. Functional, okay? This is an object that takes a path and gives you a number. It's a functional. This is not the classical action. The classical action is the integral of the Lagrangian along the classical solutions. That's the action functional. It's a different thing. But still, we know that to formulate a classical theory, I can start with the Lagrangian, I can start with the action, and minimize the action, or extremize the action. But this is the action functional, therefore this integral is a functional integral, and that's what we call Feynman path integral. Now, everyone, what I'm doing from here to here is putting names to extremely ill-defined objects, just putting names. So the intuition here is that, okay, I'm integrating on the space of paths, because this here is a path parameterized by the time. So I want to go, this is time 0, this is the time S, that's the final time here. I want to go in time from 0 to t, and I will use a poetic license here. I would refer to the particle goes from here to here. Be very careful. In quantum mechanics, the particle doesn't go from anywhere to anywhere. I measure the particle here, and I measure the particle there. What happens in between is our imagination. And so I'm calculating the probability amplitude to go from here to here. And this, the intuition here is that I go over all possible paths, satisfying the boundary conditions specified by the arguments of the propagator. I calculate the action of each of these paths, which is not the classical action, it's some object that I obtain out of my path. I take my path, I put it into that object, integrate gives me a number. I put it there in the exponent, and I sum over all possible paths. And that's it. This is the kind of Feynman picture that we all know and love, and I will stop there. Now, this formulation is what we call the Lagrangian formulation. Why we call Lagrangian? Because the object that I get here inside, this guy, well, is the Lagrangian, which depends on your path, your velocities, And for time, for systems which do not depend explicitly on time, that's it. Very quick. You can generalize this, of course. More degrees of freedom. Well, that's very cute. More degrees of freedom. You have many components of Q. This has many components over Q1, Q2, Q3, Q4. This has many components. This has many components. You know, this is like that. Many, all that. This is many degrees of freedom. Very easy. Well, expected, but very easy to do. Time dependence, please. This is, no, they are, this is a system of particles, but they can be perfectly interacting, no problem. This potential here contains the external potentials and the interparticle potentials, no problem. This is a very important question. In this formulation here, the number of particles can be whatever you want, but you are not making it go to infinity, okay? Which is what I'm going to do here. So this is still the number of particles is kept finite. And there are some other things. If the particles are indistinguishable, I have to do something on top of this, because I have to do something with whether they are fermions or bosons. So I have to introduce these anti-symmetrization of symmetrization operators and all that, and get extra sums around. But I mean, the physical picture of the system here is a bunch of particles in real space, and they can be interacting. Excellent question, thank you. Very important. Okay. Where I was. Time dependence. Remember that in operator quantum mechanics, time dependence is really bad news, right? The time evolution operator is impossible to calculate, except if you do some time ordering. But with path integrals, the problems are still there, because calculating path integrals is hard. But at least formally introducing time dependence is super simple. The potential depends on time. This function here depends on your path and the time, and that's it. The path integral looks exactly the same for time-dependent potentials, which is one of the advantages of working with path integrals. Okay. So we are done with our standard construction of the Lagrangian form of the path integral. I will come back now to one particle, and I will introduce a different way to construct the same object, which looks bigger at the beginning, but has its advantages. So I need you to come back here. Please. In the denominator? Here? Here? This. Well, there is, well, it's a highly oscillating term, but it's not a function of Q initial, Q final, and the time. So you blame all that mess into this measure. Now, to be very specific, in this formula, 1 over I, or let's do it better, 1 over square root of I is e to the minus I pi over 4. So in this formula, at least, this is the branch of your square roots and all that is very precisely defined. But yeah, I mean, this measure contains these factors. I don't have time to go into that, but when you use the path integral and you know what you are doing, you go by the book and you, for example, you want to calculate a propagator. There are ways to do it. There are a school of people, like I know at least Rodolfo Jalabert, a dear colleague of ours, says, this thing doesn't exist. This thing exists. So when he has to calculate a path integral, he discretizes. And then you have this thing here. You take the limit n going to infinity only at the end of the calculation. And if you are lucky, then there is no issue at all with anything diverging or anything. I think that path integrals can be also objects on their own. But then these kind of questions appear somewhere. And this somewhere is a process that you need to implement when you calculate functional objects like that, which is called regularization, which is essentially dealing with this kind of undefined things. So if you take this serious, certainly this object contains a e to the minus I pi over 4 times infinite. Sure. And the amazing thing is that you go and do this for specific problems, and there is another e to the minus I pi 4 with infinite minus 2, and you end up with 1 or whatever. Yeah, yeah. But you have to go and regularize, certainly. And I cannot go into that right now, but I'm willing to give you some references on that. Mm-hmm. Okay, let's move to the Hamiltonian. So we were here, and instead of calculating this integral, well, I will keep the integrations over momentum. But you see, every time you split, every time you introduce a unit operator in position and do this, you have to introduce also a unit representation in momentum, and I will keep them all there now. So the idea is again the same. I will just give you the result. Mm-hmm. Okay. So please remember that. Now, I will keep the P integrations, meaning I won't solve the momentum integrals every time, and I will show you the result that you get. That I guess you have already the intuition, but let's be pedantic and write it explicitly. So I have a bunch of integrals over, the indexes are important here, from minus infinity to plus infinity. Then I have a bunch of integrals I think I will write the short version because I'm going too slow. I have a bunch of integrals over the q's as before, but now I have integrals over momentum. Bunch of them. And one little guy here that is annoying but doesn't change anything. What do I get here? Look what happened here. In this integral, I have like the kinetic energy again. I have the potential energy before. Pay attention. Minus here, minus there. So I still have the Hamiltonian. The magic in the path integral is that when you perform the momentum integral, instead of minus kinetic energy, you get something like that with a plus. And that's why eventually you get the Lagrangian and not the Hamiltonian. But at this stage, well, I have all these factors. I have all these factors and these plane waves coming from here. So I will write it like that. Sorry. It's too far away. Pj, Qj plus 1. That's it. I'm just doing the same program, but keeping the integrations over momentum. Well, okay, when this sounds kind of something that I can again consider in the continuum. So let's introduce symbols again. Very important, again, in this expression, remember always, Q0 is Q initial, Qn is Q final. And now you should be able to notice something very important. Well, I still put conditions only on Q. You see, the momentum integrations, all momentum here are integration, or momenta here are integration variables. And so let's introduce this cube notation. Which conditions I'm imposing? At initial time, Q is Q initial. At final time, Q is Q final. And I hope you recognize here the discrete version of the following integral. And you recognize here the Hamiltonian, the classical Hamiltonian, which in this case I obtained simply by removing hats. The classical Hamiltonian is no hat here, no hat here, no hat here. And this turns out to be precisely what you get here. That depends on Q and P. Well, what we have achieved here is something that from your lectures in classical mechanics should be very transparent for you now, which is, if you remember from classical mechanics, how to go from the Lagrangian to the Hamiltonian, this is how you do it. So, short reminder of classical mechanics. Remember that the Hamiltonian is defined, you start with the Lagrangian and define the Hamiltonian by what is called Legendre transformation. P, Q dot, that depends on Q and P, minus Lagrangian, that depends on Q, Q dot, that depends on Q and P, where this object, the relation between dots, Q dots and P, with, you define P as a function of the coordinates and the velocities as the derivative of the Lagrangian that depends on Q dot with respect to Q dot. So you start with the Lagrangian, define the momentum as this derivative. This is some function of coordinates and velocities, of coordinate and velocity, and then you invert that relation to obtain the velocity as a function of coordinates and momentum, and this defines the Hamiltonian. So well, this makes total sense. The action is the integral of the Lagrangian. The Lagrangian I can write in terms of coordinates and velocities, or the action can be written in terms of the integral of this combination involving momentum and coordinates. And well, that's why I call this Hamiltonian formulation. Well, because now I have explicitly the Hamiltonian here. Why is this important? Because as I will show you very briefly now, and you can look in the books on many particle systems, this construction passing through the Lagrangian depends on me being able to calculate this type of integrals. But I can calculate these integrals because the kinetic energy is very simple. It's P squared. If you give me a kinetic energy which is P to the 4, you cannot do that. And then you say, oh, the path integral doesn't exist. No, it exists, but not in Lagrangian form, in Hamiltonian form. So Okay, we start 9:30, right? Okay, so yeah, we are going fine. Sorry? Yes, yeah. So that's a good point to ask. How are you doing? Everyone, are you following this? Really? Okay, great. I'm super happy to hear that. Well, but if you take this road, you can always tell me, hey, Juan Diego, man, but you know, you claim that this is more general, but you strongly and brutally rely on, again, this representation here with the p squared and all that. So now we will liberate this from the p squared over 2m plus potential, and we are going to do general Hamiltonians. So we know what is the trick now. To do general Hamiltonians, we need to introduce both coordinate and momentum paths. But remember, the propagator lives in configuration space. The momentum are only integration variables here. The momenta are only integration variables. So very quick. I will do something that is a even more dirty trick than the one I did before, keeping these epsilons and all that. We will consider these kind of matrix elements now. Right? I know that I take the propagator, split it into pieces. Each of these pieces, I put a unit representation in coordinate, and nearby a unit representation in momentum. So I end up with a bunch of objects like that. Okay. If epsilon is small, one expects this to happen. Actually, this is really correct. For bounded operators, this is correct, but the Hamiltonian doesn't need to be bounded, especially from above, so that's a delicate thing, but one expects this. Again, I expand the exponential up to a first order. Now, look at what I'm going to do. This QP with this Q, with this P, with this 1 here, let's do it right. This is one operator. Gives me simply this. And then I have this guy minus I over h bar epsilon Q H P. And now comes the trick. Look what it's not a trick. And this has an error that goes to 0 and epsilon goes to 0. I don't like to put powers there. Okay, at this stage, if you want, yes, but eventually, when I multiply all these things, and I don't like to put a power there, and I can. Yes, and not only that, I mean, already at this level, this is very misleading, because actually, the thing that you are neglecting has to do with matrix elements of the Hamiltonian with respect to Q and P. And these things are not bounded. So, yeah, they are small in the sense that they have an epsilon nearby, but the prefactor can be whatever because it's not bounded. So this is very tricky thing. So that's why I prefer not to put powers, but in powers of epsilon, that's a correct step. Yeah. Okay. Now, this is very cute. Pay attention. Well, you would say, yeah, no problem. I can always do that. Yes and no. I can do that in this case because this QP object is never 0, right? It's a plane wave. There are systems in which you try to do this, especially spin systems. You try to follow this path, and then the object that you factorize here can be 0. And then everything goes to hell. So, but in this case, we are okay, because this QP thing is never 0. And guess what? I will re-exponentiate this with the same argument. That I'm making an error that is bounded by epsilon. And now, well, this looks like a terrible mess, but let's consider a couple of silly, not silly, but kind of simple examples. Let's consider our usual, I will make a box with examples here. Let's consider H to be the usual, T plus B. And the potential only depends on the, you don't have magnetic fields or anything, the potential depends only on the coordinates. Okay, then what is this? Q, H, P. Well, that's quite nice, because when I hit the momentum state with the V, well, this gives something, I don't know now, but when I hit the momentum state with the T, it gives me just the kinetic energy at momentum P. And the same happens with the potential here. When I hit it with Q, I get a number. So this is actually this plane wave times P squared over 2M plus V of Q. And if I divide by this thing, well, this goes away. And then the monster I have here turns out to be the classical Hamiltonian. So it seems like it works. So then I can put any function of momentum plus any function of coordinates, and this will happen. So for a huge family of Hamiltonians, this prescription gives you something up there, which is what you want to have there, which is the classical Hamiltonian. Fine, this. Now, bad news, the sad news. The Hamiltonians we will be most interested are Hamiltonians which are, for example, H has something like P to the 4 plus P to the 2, Q to the 2, and I need to make it Hermitian, Q squared, P squared, plus, and in general, you have very complicated, still polynomial, but very more complicated functions mixing Q and P. And when you have this kind of monsters, well, you have to start, for example, the matrix element QP of this operator, Q squared, P squared, that's quite easy, because momentum operator acts on state, position operator acts on an eigenstate, fine. But this matrix element applied to this object that is in there, well, you have to manipulate it, and in a way that all the momenta are to the right and all the positions are to the left. This is one version of what is called the ordering problem in path integrals, which is what is the classical Hamiltonian? It's not that simple like remove hats. Remove hats is good here, but in other cases not. And so you have to work a little bit on that, but this is discussed in the literature. I won't go into that. And well, I have to start manipulating this thing. And I have to be careful that the result that I get is real. We have a real classical Hamiltonian, not a complex. And so you have to think about this. This whole kind of problems are called ordering problems. And they are discussed for semi-classics. I don't need to worry about that right now. Okay. So from now on, given these examples, I will call this the classical Hamiltonian depending on QP. It's a real function, hopefully also bounded from below and all that. But okay, now we are ready. Look, I have a bunch of objects like that all around, And when I introduce my Q's and my P's, I also have these plane waves around. And if I do the whole thing again, I write all the integrals, I put them together, I consider the boundary conditions on Q, paths and all that, you get exactly this result. Okay? So we are done. We have a way to produce a path integral in Hamiltonian form. Now that is independent on the particular form of the Hamiltonian. The formal path integral looks the same, with something that I have to find up there that defines the classical Hamiltonian. Good. Okay, so that's my starting point. Good point to how are we doing over there? Okay? Great, okay. Let's move. Good. Now, what I'm going to do now is really compact, because you have seen this very well with Martin and Barbara. I will introduce the semiclassical approximation, but in this Hamiltonian form. There is nothing mysterious. The result will be exactly the same as Martin and Barbara obtained. But I need to stress a couple of points. So I will introduce two concepts here. One is the concept of semiclassical regime, and a different one is the concept of, but related, semiclassical approximation. Okay, so I will, there is an important thing here. In my experience, at least, every quantum mechanical system, even the ones for which you cannot even start thinking how to proceed with this way, every quantum mechanical system I know admits a path integral representation for the propagator. One spin 1/2, I can write a path integral. A spin chain, I can write a path integral. Top, I can write a path integral. A fermionic quantum field, I can write a path integral. They don't look like that, but they are literally integrals over the space of certain space of functions of the exponential of some action. So then, since you can have a path integral for any quantum system, well, certainly any quantum system, I can define a classical Hamiltonian, because I do my path integral and I read from the path integral, that's the classical Hamiltonian. So every quantum system has a classical limit. The problem is whether the classical limit tells you anything about the quantum dynamics. Then, for example, if you have a spin chain, you can do the path integral, you can do the identify a classical limit. But then if you look at the classical dynamics, most likely the quantum dynamics will do things which are completely different. So you don't gain intuition about the quantum dynamics from the classical dynamics for every system. Okay, a good example, a fermionic quantum field. Don't get scared by this. Is electrons jumping in a lattice and they interact. Well, this thing has a path integral, but turns out that the path integral requires introducing no like numbers like these ones, but something that is called Grassmannian numbers that anti-commute, because fermionic fields anti-commute, and that's very counterintuitive. But you can write a path integral. You open a book on quantum field theory, you will find the fermionic path integral there. The classical Hamiltonian you see from there, well, it looks like some function, but it's a Grassmannian function of things that anti-commute. Well, this has a classical limit, but I have no idea how to use it to understand anything, you see? So the fact that a system has a classical limit, and the fact that the classical limit tells you something about the quantum dynamics are different things. And what makes the difference? The existence of a semi-classical regime. So I would say that a system admits a semi-classical regime if, so a system admits a semi-classical regime if there is a chunk, a piece, a region of its Hilbert space. Don't get Hilbert space is the space of states of the system. So what I'm saying is that a system admits a semi-classical regime if there are a bunch of states, physical states of the system in its Hilbert space where the quantum evolution, the dynamics, meaning the propagator is dominated by classical paths. So you have all possible paths here, all of them. The ugly and the even more ugly, the crazy stuff you have in this space. Now, if when I apply this quantum evolution operator to certain kind of states, and to propagate those states, I mainly need the classical solutions and a little bit more. This is what we call having a semi-classical regime. And that's the problem with the spin chains. Spin chains don't have a classical regime. I can do classical mechanics there, no problem, but I gain nothing in order to understand the quantum properties from there. But a particle in a billiard that we have seen these days, particle moving around in the billiard, not every state of a particle in a billiard has this property. For example, ground states, you take the ground state, you apply the time evolution operator, you calculate the quantum mechanically exact, then you calculate it using only classical trajectories. Well, this is simply not good. That's it. The two things have nothing to do with each other. But on the other hand, a particle in a billiard has a regime where the propagator is well approximated by classical solutions in a non-trivial way, as Martin explained, which is the high energy regime. So let's call this L, the linear size of the system, and the particle has a momentum P that depends on the energy. And roughly, when P times L is large, then this means the high energy region of the Hilbert space is such that the propagation of states with those energies can be accomplished with only classical solutions and a little bit more. That's the precise statement. So there are people now in the many-body quantum chaos community that like to call systems with a classical regime semi-classical systems because they have a semi-classical regime. Don't get confused by the name. That's the meaning of that. To make it different to systems where you can define a classical limit, but the Hilbert space, nowhere in the Hilbert space, this is useful at all. There are no regions where this is useful. Okay. That's the, now if I assume that the system admits a semi-classical regime, the semi-classical program was explained in great detail by Martin and Barbara, consists on the saddle point, the stationary phase approximation to this integral. This is an infinite dimensional integral. You have done saddle point approximations, or for sure you remember the Stirling approximation. This is a type of saddle point approximation. The stationary phase approximation relies on the same concepts as in in finite dimensions. You have to look for the extremal of the function that you have upstairs, but this is infinite dimension. Probably Martin told you this, but for my taste, I mean, you learn how to do stationary phase approximation for the Bessel function, one integral. Now, to think that I can take that machinery and go and apply it to the path integral, which is already a mathematically complicated object, I think you need to be really bold and a genius, and this was Martin Gutzwiller who did that. So he went and did the stationary phase approximation for this monster, and I will tell you the 5 steps that Martin was reviewing the other day. The first thing you need is, well, you start with your path integral. Then you need to find what we call in finite dimensions a stationary phase point. The stationary phase points are, I think I will do this very quick here. You have an integral like that. Let's call it this G. And you are interested in lambda large, and G and F are well-behaved functions, derivatives, and all that. Okay, so the first thing you do to solve this integral with the stationary phase is you find the critical points of F. The points where F is critical. I have seen books in classical mechanics telling you that the Euler-Lagrange equations of classical mechanics are obtained by minimizing the action. That's wrong. You extremize the action. And really serious books say that. You extremize the action, not minimize. So you have to find these guys. You have a bunch of them. So the solution, you call it x1, x2, x3, whatever. What does it mean in the path integral? Well, the path integral means you have to find the places where the variation of the action with respect to the path. Look, I'm doing it Lagrangian. If I do it Hamiltonian with respect to the both paths in coordinate momentum, you have to find the paths Q and P where this variation is 0. And something that I'm sure Martin and Barbara stress a lot, but I will stress again because it's important, is that you know what is the meaning of that. The extremizing the action with respect to Q and P gives Hamilton's equations. And this H is the classical. I won't write anymore, but this is the classical. Okay, now, super important, don't forget the boundary conditions. That you have conditions at time equals 0, Q is Q initial, and at time final, Q is Q final. Why is this so important? Because this problem, where is my yellow? This is a perfectly well-defined, well-posed mathematical problem. Set of equations of first order with the same number of conditions. But this thing admits several solutions. And this is, you learn in your lecture in classical mechanics that Hamilton's equations have a solution which is unique. So what's the catch here? Can anyone tell me what's the catch? I'm sure that you remember in classical mechanics, mathematical theorem, if the Hamiltonian is smooth and all that, blah, 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 the solution of Hamilton's equations is unique, it's a unique path. What is the catch? Well, my claim is that this problem has several solutions. And I give you an example, top of that. There is a wall here. I want to go from here to here. This is configuration space. This is initial position, final position. I can do in a time t. So the problem here is Hamilton's equations going from here to there in time t. So I can show that I can do that, and I can do that. Two solutions. Does this mean that Hamilton's equations don't have a unique solution? What's the catch? Well, yes? Yes. Yes, and so if you remember what the professor told you in classical mechanics was the Hamilton's equations for a given initial condition have a unique solution. So if I give you initial coordinate and initial momentum, then there is one trajectory follow. One and only one. But I'm not giving you that. I'm giving you initial coordinate and final coordinate. It's a different type of classical problem, and in general admits several solutions, except for the harmonic oscillator, the free particle. Like this wall, you see, I constructed two solutions. What is the price I pay? Look, the initial momentum is different. That's why you have two different solutions. Please keep that in mind, okay? That's important for us. Because guess what? I will, spoiler, total disclosure, total spoiler here. Quantum, semi-classically, quantum interference is a manifestation of this multiplicity of solutions. They will interfere, and this is how we understand interference. So that's why this is super important thing to remember. Okay, so now you go and solve that problem. Solve the classical problem. And as I say, you have different solutions. So you will have different solutions, I will call gamma. They depend on the time, of course, and depend on the conditions. What is Q initial? What is Q final? What is the time? And you have two of them. You may have many of them. You may have infinite of them. No problem. But I have a bunch of classical solutions. Now, the stationary method, phase method, then say, you need the second derivative of the function f evaluated the solutions, meaning I need the second variation of the action evaluated the classical solution. That's very hard to find. Takes a lot of effort to actually calculate that object. But in terms of integrals, we want to be consistent with notation here. But so far, okay, this is exact in the sense that I'm not telling you actually what I'm doing with my integral. Now I will tell you what I do with my integral. I take the action and expand it locally around each of these classical solutions. So I will write Q gamma, which depends on everything there, plus something that we call the quantum fluctuations. This is exact. I can always write the action as the action with respect to a classical path. So I want to go from here to there. I can have all the Feynman paths, but there is one classical one there and another one there. I can always write my integration variables, Q and P, with respect to the Q and P of the classical solution, and then these guys are the quantum fluctuations around. I can always do that. I choose one path and I do that. Now, I will do it for each of them, and I will expand to second order. Now, when I evaluate the action functional at the classical solution, that's what we call the classical action. And we call it depends on which solution you are looking at, and depends on Q initial, Q final, and the time. Okay, I keep expanding. This is zero order. This is when Z is not there. First order in the expansion is the derivative functional of the action times Z, but this is zero because of this. So what I get is something that I will write like this. This is, I will give you references for all that. This is kind of formal way, but you can make it very, very, very explicit. What is, think about when you Taylor expand a function in some small variable set, you got something quadratic in the zero order in Z, linear order in Z, second order in Z. Well, second order in Z means quadratic. So this object here I can calculate, and in principle I can go on. I can go on doing that forever, to set to the cube, set to the 3, set to the 4. The thing is that you stop there. And this is where you're doing an approximation. If I keep expanding the action forever and do the integral over Z, well, that's it. This is the exact result. But the moment I stop to quadratic order, I'm doing an approximation, and this is the approximation in a stationary phase approximation, that you stop at what we call the Gaussian fluctuations. Thing is, the corresponding object, the corresponding integral, quadratic in Z, can be evaluated exactly, because the one thing that we know how to do is to do path integrals with quadratic functionals. This we can do. We know how to deal with that. So this can be, the integral of fluctuations can be done. And the method tells you you have to sum over all possible extrema of the potential of your function. And I can then write down what Martin and Barbara wrote last week again, but a little bit fixing my notation. So the result of that monster calculation is well, stationary phase methods say you have to sum over all the solutions, meaning sum over all solutions of this classical problem. So I will sum over gamma. Gamma are the solutions of the problem of going from Q initial to Q final in time t, classically, with the Hamilton's equations, the classical solutions. Get some prefactor, which is some smooth function of Q initial, Q final, and the time. And I get the classical action of the corresponding path. And I get a bunch of prefactors and phases. I will write it just once. I won't go into details, but this all can be computed based on the classical dynamics of the system. Well, that's how we make the turn to do semi-classics, not based on Lagrangians, but based on Hamiltonians. That's what we are going to need next. And the result, of course, is the same as you do it for Lagrangian Hamiltonian. It's the same because the integration over momentum is something that you have to go and integrate. They are not producing new physics there. But the Hamiltonian formulation, you can start with very ugly Hamiltonians. And that's important for the bosonic thing. Great. Wow. Okay, I have a minute, and then I just need to, I have a, we are ready now to try to go into this. And let me briefly justify what is the idea there, which is, if I have one particle and I want large actions, typically what I do is increase the energy. But of course you can tell me if you want large actions, okay, why large actions? Because this is justified as long as this divided by h bar is large. So I need large actions. This is kind of the folklore. Okay? If you have a piece of Hilbert space where you can associate large actions, then you can do semiclassics. And so kind of the realization of this H bar cannot go to 0. H bar is a number. What we say, and I'm sure Martin stressed that and Barbara, is that what I mean by that means a typical classical action is way larger than H bar. And now we are talking, this is an action, this is an action. And for one particle, then you typically increase the energy, increase the momentum. And, but of course, you expect also that the mean energy of the system tends to increase when you increase the number of particles. Typically, of course, you have things like gravitational systems. This argument is not so clean, but like for not very nasty potentials and all that, when you increase the energy, well, the action increases. When you increase the number of particles, the energy increases. So, of course, a way to get large actions is also to increase the number of particles. That could be. But in this formalism, the number of particles is by no means easy to change the number of particles here, because the number of particles tells you the dimensionality of these objects. This vector is n-dimensional. So if you change the number of particles, you completely change the propagator. Completely is another thing. So to devise a formalism when the number of particles is something that you can change is one of the big advantages of working in Fock space. And so when we come back from the break, we will, let me see, yeah. We will start with that, with the semiclassical theory in Fock space, starting with the patent. So how are we going? If, yeah. Yes, I completely agree. I mean, these semiclassics is that's terminology, but I prefer to call these semiclassics first quantized semiclassics because it's based on the first quantization formalism. That is perfectly able to describe many particles, no problem. But the problem that we found doing that is that if the particles are distinguishable, perfect. The propagator is simply a large propagator with many Qs, many degrees of freedom. And of course, that's very hard to solve, but I can write down everything. I can do my semiclassics there. But the moment the particles are indistinguishable, then in first quantization, you include indistinguishability by explicitly anti-symmetrizing or symmetrizing things. And then I don't know how to do semiclassics there because I don't have an integral. I have a sum over integrals. And this sum, responsible of the permutations and the symmetry, I cannot give a semiclassical interpretation. If you go to Fock space, then because of symmetrization, you have to change the space where you are, as you know, but because in second quantization, the symmetrization still allows you to write the propagator as a single path integral. I don't have to sum over permutations and all that. And then I can do my semiclassics directly. I close my eyes and do stationary phase. That's really how we end up doing these things. And that's why this is a theory for bosons in indistinguishable particles. The first quantization approach, when the number of particles get large, the sum over permutations kills you very, very quick. It's transforming an untractable problem. So the semiclassical theory for systems of distinguishable large number of degrees of freedom, I think that's pretty much an open problem right now. It's very hard, very hard. And this will be easy. Thanks, that's an important question. Please. Well, in my experience, I say, every system I have dealt in my life, I was able to write a path integral. Yeah. Well, there are two aspects of this question. One is that, and I have this in my notes, and I decided not to mention it, and this is an important point, and I thank you for the question. Take a look here. The path integral representation and eventually the semi-classical approximation, they don't touch all the kinematic aspects of quantum mechanics. So you see, the space where you are is still a Hilbert space, not the symplectic manifold of classical mechanics at all. So superposition principle, entanglement, all that, well, it's kinematical. It's not dynamical, it's kinematical. So all the mathematical structure of quantum mechanics, I didn't touch it at all. So in that sense, I'm not, if I only have classical mechanics, it's what happened with the founders of quantum mechanics. They did have they have classical mechanics. They didn't have Hilbert space. They didn't have linearity of quantum evolution. And so you can go only up to certain point manipulating classical mechanics to try to extract quantum information, unless you supplement the quantum structure by postulating it. And that's why we postulate the state space of a quantum system is a Hilbert space. It's not a symplectic manifold. Now, that said, this thing, the fact that what you have here, well, one thing is for sure, the thing that you have here, this object, well, it's classical. I don't see any operator there. It's a functional. It's a classical functional because it's an object defined in the space of paths in real space. There is no operators, there is no states, nothing. So in that sense, this object is classical, is even more, is defined through what I call the classical Hamiltonian, great. But what you do with this guy, look what you do with this guy when you want to do classical mechanics. When you want to do classical mechanics, you extremize the action and get your classical solutions. Here, you integrate over all. So certainly you are doing something very different, but if there is a principle in physics that kind of puts together like different branches and structures in physics, is certainly the use of the action. Because with the same action, I can do classical mechanics and quantum mechanics, but you have to be then, oh great. You have to be super careful because when you say with this action functional I can do quantum mechanics, you are assuming that you have a Hilbert space, a time evolution operator. In classical, of course, there is nothing in classical mechanics suggesting you that you need to introduce these things. This is how it's quantum mechanics. I don't know if this addresses your question. Great. Please. Yeah. How can? Well, there is, let's say, there is two aspects of it. The conceptual aspect is I take my quantum state, put it to evolve with the exact quantum mechanical, well, this is also exact, but I use operator methods, or I solve the quantum mechanical problem exactly, and I put my state to evolve. Then I take my propagator, exact, I do the stationary phase approximation there, and, well, this is an approximation, and it's based on classical solutions. The dominating regions in path space contributing to the semi-classical propagator are the ones around classical solutions. And I compare the two. That's, of course, then you, so what the hell do you need semi-classics if you are already solving the quantum problem to define the semi-classical regime? No, this is a very kind of demanding definition of semi-classical regime. In practice, we check this. You take a look, and this was a little bit stupid, I'm sorry. This is like a typical action. You estimate the action of your system, and for example, a particle in a domain is energy gives you typical momentum times typical length, that's an action. This is actually how we do it. And then if this is satisfied, most likely then the semi-classical system has a semi-classical regime. And this is good because I don't need to solve the quantum problem to check this out. I just go and check it, and then, well, what we do, we close our eyes, do a stationary phase, use the semi-classical propagator, and since the machinery used to derive the semi-classical propagator is based on asymptotic analysis has some, it's kind of magical. Many, many times, asymptotic analysis gives you way better results than you expect outside the official regime. For example, semi-classic gives you correctly the ground state energy of the hydrogen. This shouldn't be, but okay, there is some freak of nature there, but.
In the drawing that you made there, I see that you have a magnetic flux there. Inside the triangle. Inside the triangle, you have a magnetic flux. And then you will have a particle code effect at the final point.
Yes.
In quantum mechanics. And in classical mechanics.
Sure, sure.
I mean, I think that there the difference is that the initial conditions that you put in classical mechanics and in quantum mechanics.
The initial.
Quantum mechanics, it's really, you want a final point and initial point. And in classical mechanics, you want initial conditions.
Well, I don't. I don't. I'm perfectly happy with the shooting problem. Really. This is how I think, let's say, in terms of initial and final. Okay, no, but I mean, we use the classical paths, and
So in the classical path, you have a interference in the final point. For the probability to find, your example, you started in the left,
yeah.
and that in the top one.
Yes.
You have two alternatives around the magnetic flux.
Yes, but the thing is that the magnetic flux term is a piece of the action.
That's right.
Okay, and
Classical in quantum. It's also in the classical action. You use also in a classical action, you also use
yes, but in the classical action you don't feel it, right? In the classical equations of motion you don't feel it because.
It has to be there. I mean, that's your classical action.
Well, but it's a delta. I mean, a line of flux is a delta in the classical action. So if you don't pass through that, you don't feel it. In the equations of motion, you don't see it, unless you construct a path that passes through that.
Well, A vector is everywhere. The magnetic field is
Yes,
yes.
yes. Yes, but classical mechanics doesn't care about the action. Classical mechanics cares about the equations of motion. And in the equations of motion, what you get is the magnetic field, which is a delta at this point. But the action cares, and that's why quantum mechanics cares, certainly. This is exactly my picture of that. Yes. But okay, you know better than me about that. So it's an interesting discussion that we should have in front of everyone. Yeah, of course. I mean, please, any question, comment, most welcome. Then I see you in half an hour. Is how?
Yeah, in 20 minutes.
You would have to stand me for a whole marathon. Thank you. You have to fix things there. Oh, really? Did I tell you that? Sorry.
No, I mean, in the very beginning you said 2 weeks, and then I thought, okay, you can give your talk now. So that's why you have to give 2 now.
I never told you about that I would be in Rio.
I did what I thought, but I mean, that's now you are punished by it now because you have to give 2 talks.
Yes,
one
but
after
why?
the other.
How did you get to know that I was in Rio last week? Because
You wrote me
I
an
told
email.
someone.
You wrote me